Is there tea in your place? Kyoko, there's no tea in Ukambani. I don't need to bother you. Kiptum, Sandra, is there tea in your place? You want to compare notes? Anyone who knows what they use in the tea factories? Alan, is there tea in your place?
No.
Anyone who can tell us? Kikwech, is there tea? Or you have no experience with the tea factories? Anyone with experience with the tea factories, what they use? Okay. Otherwise, they are still classified as hydraulic machines, which is a very broad term because it covers very many things. We love pumps under that. Turbines also, we have turbine pumps. Like I've said, we have fans. They are put under that classification. We do have compressors. We have blowers. And if we go to a deep detail, we have what we call fluid couplings. Okay? We have fluid couplings. We have torque converters. In other words, we have got what we call converters. We also have identifiers, though they may not fall under that classification. Okay, if we go far, we can talk of jib and the crane. Jib and the crane, you come across it in the construction industry, though they may not fall under this kind of classification. Suffice it to say that these hydraulic machines, calling the centrifugal pumps, they convert mechanical energy into electric, or rather into hydraulic energy. Which is a sort of a form of pressure energy, where we convert the mechanical energy into pressure energy by means of that centrifugal force. For that reason, we maintain the name centrifugal pumps. Further to this, they can be classified on the basis of their head, that is pressure head or pumping head. I'm sure you understand when I say that. They can be low head pumps up to 15 meters. And in that case, you come across them, they'll be using a volute casing. They can also be medium head pumps, up to 40 meters of water. That is meter heads against which they are pumping, which we can be able to convert into pressure head. Yeah. Why is it so? Because meter heads, let me call the meter heads. Let me put that in brackets. Meter heads, they are given by what I'm going to insert right now. Okay, just to remind you, lest you forget. Oh, what is this? Okay, let me remove this. Don't like that underline. So that one is pressure head. When you divide that by density of the liquid and the gravitational acceleration. That is what we call meter heads, which is equal to H. Okay? Though you know that when it comes to pressure head, please allow me to digress a little bit. As a reminder, lest you forget. What we call pressure head or what we call pressure rather, that one is given by rho H. I'm sure that is clear to all of us. Let some of you say, you know what you're talking about. We talk of meter head. Pressure head in meters. We say meter heads. Meter head. You leave it at that. It is actually given by that kind of an expression. And that's it. So they can be classified as low head up to 15 meters, medium head up to 40 meters head of water or whatever liquid is being pumped. And at the medium head, you come across the diffusers, the diffuser ring, and then we have got high head. These are pumps which operate against a head which is more than 40 meters. They are usually multi-stage, though we still have others which are single stage, and they operate with more than 40 meters. Okay? They are high head pumps. I did say we can classify them on the basis of casing, where the casing is the housing of the impeller. And it is that housing of the impeller which supports the shaft, and the shaft has the bearings. We talked of volute casing, the diffuser, and the vortex whirlpool. We can have that kind of a classification of centrifugal pumps. We can also do it on the basis of the direction of flow. We have done said we have the radial flow pumps. We have the axial flow pumps, and we have mixed flow pumps. This could be one and the same thing, but then it depends on how water enters into the pump and also leaves the pump to dictate whether it is axial flow or mixed flow or radial flow. Still, my old pump, we can't afford talking about to fair, or we cannot afford not to talk about it, which I've said is a simple thing. You can see the volute chamber, okay, or the volute chamber. So outside there must be a volute casing, and you can see the outlet and the inlet. You can see the drive shaft position, and you can also see how the direction of rotation is indicated. Casing or the pump casing. We have done said and mentioned that before you start a pump, if it is a simple reciprocating, centrifugal pump, you have got to prime it. You have to put water inside. Meaning, if you look at the details of construction of the pump casing, it is built with provision for putting water before you can start pumping. Once it is full of water, then you can run the pump. And if all the mechanics are in the right way, then it will run and give you the kind of a liquid you are looking for. Okay? We also have other type of pumps. Like you can see what we have here. It's much more of, this one tends to fall under the classification of the reciprocating pump. But suffer it to appear there because it has some kind of a rotor inside. It has the mechanical seals, it has bearings, and many, many more details where you have the inlet and the outlet. Okay? We have also a rotor with a starter, whereby you can see the inlet and the outlet. It is a compression kind of a cell, and we still bring it under this kind of arrangement where we are talking of centrifugal pumps. I said the suction of the centrifugal pump as a foot valve in a strainer unit. Okay? It is the foot valve and the suction pipe and the strainer which are dipped into the water sump, because it is held by the lowest part of the suction pipe. Dip it inside, and with all the other arrangements, good, to avoid cavitation. Then if the pump needs priming, you prime it. Once you are satisfied with the priming, you can start it and continue with the pumping exercise. I've said that a foot valve is usually found at the end of the suction pipe, below the end of the suction pipe, and below the foot valve is actually the strainer. The delivery pipe is connected to the outlet of the pump, I've said, and it delivers the liquid to the required height. Therefore, we simply refer to it as a delivery pipe without going into the other details of design. We've talked about the pumping principle or the working principle, where I've said the pump does nothing to lift the liquid from the pump to itself, but you create a situation where a vacuum is actually induced, and with an induced vacuum, atmospheric pressure acts very fast, pours the liquid through the strainer, the foot valve, into the suction pipe, comes across the rotating element and it is given that pressure energy so that you can pump the liquid to wherever it is required. That is the basic principle. Okay? And that's why all the time, unless the pump is said to be self-priming, we have to fill it with water and a special centrifugal pump in the suction pipe all the way into the casing. And possibly we can allow it to move up to portion of the delivery pipe, maybe up to where the non-return valve is, or what sometimes they refer to as the delivery valve, where it is removed from the casing, and then you create a partial vacuum, which nature abhors, and then the atmospheric pressure will act very fast to raise the liquid through the strainer, foot valve, and the suction valve right into the pump casing. Okay? You will denote, or you will discover, let me put it that way, that the pressure generated by the pump is directly proportional to the density of the liquid which is being pumped. That is something that you can be able to ignore. Okay? But let's move on. We'll see where we can be able to bring it in. And then we can have it as a part of other details which will help us facilitate in pump installation. Remember, the priming we are talking of has to be done properly. And when that is happening, the delivery valve is usually kept closed. And up to the time you start the pump, the delivery valve is kept closed. You run it as you monitor the pressure gauge on the pump side or the suction side to see whether it will lift the pressure to the stipulated working pressure or it is going beyond. And then you turn the valve, you open the valve slowly, not quickly, because you do it quickly, you create a scenario for water hammer. And that way you may break the system. You live to blame yourself when that happens. Okay? Otherwise, you remove the air from the casing to have a partial vacuum, and then the pressure is generated proportional to the density of the liquid. When you start the prime mover, you run the pump with the delivery pipe still closed. I've done told you that. I see whether the pressure maximum. And then you start turning the valve slowly until you achieve a full throttle in the delivery. On your right hand side, I don't know which side you're looking at this one, you can see the kind of arrangement I'm talking about. You can see the suction pipe. Yeah, you can see the suction pipe. You can see the foot valve with a strainer, and you can see the casing. Okay? And you can see also the impellers inside the casing, which we are calling outer periphery of the impeller. And then there is the primary funnel, which facilitates in priming the pump. You can see the position of the delivery pipe and also the positioning of the delivery valve. This is a simplistic way of installing the pump. Okay.
Excuse me, sir.
Yes.
In the previous slide,
With this one.
yes, you
Mhm.
said before you start that pump, you have to fill it with water. Is
Yes.
okay? Is it done manually? Is it that a person comes, fills in the water, then you
Yes.
run the pump? Or
Yes, you do it manually. Unabeba do unaweka.
that is tiring.
No, it is not tiring because it is a one thing. It's part of starting the pump. If not, you buy a pump which is self-priming, which are very rare to come across, and then you don't have to do that kind of an activity. But in agricultural fields, I don't know where you come from. If you go to Mwea irrigation scheme, that is what most of the farmers are doing. I'm also doing it. I'm doing irrigation on my farm. I have this kind of a pump. And you can come across me making noise when guys have not primed it and they want to start it. Maybe you come for attachment in my field. I show you how we go about it.
I have a farm of my own.
Yes, thank you. And how do you don't you use what?
I don't know, rain. Okay.
That is what we call rain-fed agriculture. Okay. But if there's a river nearby, you can stop limiting yourself. You get a small pump or let someone get you a small pump, depending on the irrigation field that you are putting under cultivation. And you can grow crops in season and out of season. Do you think that's a good idea?
It is.
Yeah, kwa hivyo tukutana wote tukienda tutanunulia sisi lunch na chai huko nje. The proceeds from farming. Thank you for that. Otherwise, it is not tiring. This is what you do. Even the small palms you get from Davis and short leaf, or the ones you get from suppliers, it has a provision for priming. Lazima ufungue, and then you prime it, you put water, then you run it. Otherwise, even when you are dewatering in construction sites, you have done dewatering in foundation engineering, or you don't know that. How many have come across a dewatering exercise in a foundation engineering, in a foundation where you are putting up a foundation? Because you go excavating, either for a basement or foundation, and find there's a lot of water. How do you get rid of it? You get these small pumps, you install it, you prime it, and you completely dewater the foundation so that you can be able to cast concrete. Anyone with that kind of experience?
Yeah.
Yeah, that is what you do. And you can even have a multiple of them depending on the amount of water. I wish you saw when they were putting up the Tans Tower, they hit an aquifer. I'm sure you know what an aquifer is when you have done groundwater in your water resources. They hit a very rich aquifer, depending on how deep you are going with your basement. And when you hit that rich aquifer, you must have a pump which you drain it completely so that you can be able to cast your concrete for the foundation. Huh? Sometimes you go for use of chemicals to freeze the water in the aquifer so that it doesn't flow into the excavated site. But outside of that, this is what you have to use. Okay, you have to dewater the foundation trench before you cast your concrete. This one, whether you like it or not, you come across it. Even on road construction sites, you reach a point you find you have to dewater before you can do anything. Otherwise, will you work in what is only in the construction of bridges, where we use diving bells and we use caissons, okay? The pneumatic whatever caissons, so that we can construct, unless you go for Kufa dams, where you isolate an area, you construct, but then still you have to dewater, whether you like it or not, okay? All this is construction. These are techniques of construction, depending on what we are constructing. Otherwise, you don't get tired of this. You have to prime the pump before you start it. Another question. Okay. We still have the components and construction of the same. You talk of the impeller, it is a wheel or a rotor, which is provided with a series of backwards and forwards blades, or we call them vanes. It is mounted on a shaft, which is horizontal, or it can be vertical depending on the installation of the pump. And it is that shaft which is coupled to an external source of energy, which could be an electric motor, or it can be coupled to a diesel engine. It can also be joined with that diesel engine by means of belts, or it can be directly coupled. You can have them mounted on a common base plate. You have the same base plate, which has a metallic plate. You mount both of them on. And then from the common base plate, you run the pump with the engine. Okay? It is only where you use electric motor, which is a bit clean. Not a bit clean, it is clean. Okay? Otherwise, the suction pipe connects its upper end to the inlet of the pipe, of the pump. And then the lower end will dip into the water. That is what we call the sump. Like you can see this kind of an arrangement. In this arrangement, you can see the sump. You can see the position of the foot valve and the strainer. The strainer is just a kichungi, if I may use that language. The strainer is just a sieve or a kichungi to put off debris depending on the quality of water. And then you can see the suction pipe. You can see the suction fledge. That is the kind of joining of the pipes with the pump. You use a fledge, or else you can use other fittings. You can see the vacuum gauge, where it is positioned. And you can see the pressure gauge in this setup, where it is positioned. This is what I was telling you, and you can see the impellers. The eye of the impeller, you can see the position of it, which coincides with the shaft. And then there is the casing. Okay? In this case, the pump can be driven by an electric motor or oil engine oil, or diesel or petrol, whichever, depending on the size. And then you can see at the delivery fledge, there's another pressure gauge, because it is that delivery valve, you close it. When you prime the pump, then you start it, let it run until the gauge hits maximum. Then you start opening the valve slowly so that you don't induce water hammer. Okay? You run it slowly, you open it slowly, until you hit the maximum. And you can see the gauge come down until it reaches the operating position. Okay? You can see the delivery position of the delivery valve and the delivery pipe and the overhead tank, whether it is 10 kilometers away, 20 kilometers away, or 5 meters away, depends on the distance. And then you see the discharge level. In this arrangement, what can you see? From the free surface of the sump, you can see HS, which is the suction head. Inside the suction pipe, you can see VS, which is the velocity due to suction. And of course, you have seen the voot valve, the strainer, and the suction pipe. Okay? This, depending on how the impellers are arranged, it is likely to be maybe a diffuser type, if not a vortex type. We'll be able to see, to look at those details. Then after that, what do you have from the center line of the pump? You have HD, that is the delivery head. Delivery head is given by the elevation height due to elevation, plus all the friction losses, because it has to overcome the friction losses. This is where the friction losses matter so much. It is also in pumping. Remember, I told you when we are doing friction losses, it is in pumping where you have to account for all the friction losses, minor and major. Because those few millimeters you may ignore because they are minor losses, may deny you the liquid. Here you don't gamble with anything. You don't gamble with anything. There's no gambling in this. You have to put everything in its right position. Pumping is not a child play. It's a serious matter. Okay? So this is the same kind of an arrangement, but more detailed than this. This one gives you a primary funnel for priming, which my friend doesn't want to, she feels it is tiring. But whether you like it or not, you may have to do it. Because even the pumps that you buy, they have a provision for priming. Kuna shimo ya kuweka hiyo maji, whether you like it or not. Okay? And that's a good arrangement. Now, when it comes to that element we're calling the impeller, we are looking at it in a little bit more of details. We said it can be open, it can be closed, or what we call shrouded. It can be shrouded or surrounded impeller. The shrouded one or the closed one is for liquids that are pure. What do we mean by purity? They are completely free from foreign matter, debris. Okay? You use closed impellers or shrouded or surrounded impellers. Okay? When it is semi-open, not completely open, not completely shrouded, you find the veins are fixed on one shroud plate only. You break one, and that's why I think we should take an afternoon with tour mechanical. I'll go there first and check what they have before we can make a tour. The veins are fixed on one shroud only, if it is semi-open. And this one, you can use it for pumping liquids, which have debris up to a certain extent. In other words, they may be used for pumping of sewage. They may be used for pumping of coffee pulp or vapor pulp, etc. You can have the semi-open impellers. The pump can have impellers which are semi-open. You can see the meaning of it being semi-open, that the veins are fixed on one shroud. When it is fixed on both shrouds, it is a closed kind of impeller or surrounded. If it's an open impeller, it means the veins are fixed from one center with a web plate only. like you can be able to see, or you'll be able to see. There'll be no crown of shroud plates used. And this is, the open one is for pumping those liquids, which have a lot of debris, coarse materials, coarse debris, or mixture of water, sandy clay, sandy pebbles, or even sewage. Sewage has a lot of things. If you go to an outfall of a sewage treatment plant where it joins the pipeline bringing in. I don't know whether Kariobangi's sewage treatment work still operates. You used to see very interesting things when you go there. It could bring all sorts of things. The good news is that it has got screens which you can wreck or clean up mechanically, or you clean them up using some hand tools. Then after the Rex, it has a grit chamber. After the grit chamber, you have the detritus tank. From the detritus tank, you go to the primary sedimentation. From primary sedimentation, you go to secondary sedimentation. From secondary sedimentation, you go to the trickling filters. But in between, you may find installation of a pump. Like in Kariobangi, they used to have a reciprocating pump. Then after all that, you either recycle what has gone through the secondary thing or what has gone through the trickling filters. You carry out what we call activated, you come up with an activated sludge system, okay? Where you try to seed what is coming in so that you can be able to hasten the biological process of degradation. Then from there, you have the solid matter, which you take to the digesters. Still, they may have to pump to the digesters because I don't see it flowing by gravity to the digesters. Then from the digesters, I don't know whether you pump it to the drying beds, where you get rid of water in the sewage, where you create a sludge cake and there is a sludge liquor, which you separate. The sludge liquor, you can take it to the system because it is ripe with bacteria for biological treatment. Anyway, this is still a combination of all this. We are talking about pumping, not public health engineering. So these are a few of the impellers. You can see the veins. You can see the positioning of the shaft, the web plate. You can see the eye of the impeller in a very simplistic way. You can see when it has one shroud, it looks like. The vein has one shroud, which is mounted all the way up to the shaft. And on the shaft, there is the bearing, so that the thing does not run and runs wobbling. Any questions on that before we move on? Any question? Collins or Mondi? Collins, are you still there? Or you have gone to sleep? Collins Mulinge, can you help the other Collins? Are you okay? Oh, you have no questions. Feel free to ask questions. Mondi, umeenda wapi? Na hiyo kelele. Mondi, where are you operating from? I want to hear your voice.
I have no question.
Yeah. What of Mercy Mundi? Any questions, Mercy?
No questions.
Good. Let's move on. And if there's no one, what of our big men, the one and only Desmond Tutu? Desmond, any questions?
No.
Good. So after we have seen the kind of impellers we'll have, I'll give you others with more details. Then we have the various types now. We have the vortex type, you can see. And that's why I was telling you, whatever we have here could be a vortex type. You can tell that now from what you can be able to see. Because here we have the vortex type. We have the volute type, which is in the middle. Okay. We have the diffuser type. Okay. And we have the vortex, we have the diffuser, and we have the volute type. You can see the difference between the arrangements of the impellers. You can see how they look like. Okay. You can also see the arrows showing the direction of rotation. Otherwise, it is on the impellers, the vanes are mounted, and it has got what call the guide blades. And depending on the arrangement of the type, whether it is whirlpool, diffuser, or vortex, you come to see later on the amount of efficiency they give you, where you have the output and the input to give efficiency. We don't go into the details of what we used to call mechanical advantage. I think that one used to do with pulleys and things like that. But this one will stop at efficiencies. And we see which one gives us the best output. The best output is judged on the efficiency. Some of them have efficiencies up to over 90%. And the poorest you have, they have efficiencies up to 50 something. The least up to 40 something. Who would want to operate with that? But sometimes you have no choice, because if that is the only thing which is available, then you may have to work with it. Now, when you talk of the vortex casing, we say it is an improvement of the of the volute case, of the volute casing. It has a vortex chamber or a whirlpool kind of a chamber between the impellers and the casing, as you can be able to see. Liquids will enter the vortex chamber from the impeller with a whirlpool kind of a motion. And water particles will have or behave like as if they were sprawling kind of a path because of the vortices or the vortex arrangement in the chamber. Okay? Looking at the diffuser, it has what we call diffuser rings with guide vanes, okay, surrounding the impeller. The guide vanes are made in such a manner that they will provide a gradually enlarged passage for the flow of water. You can see in the last one, and the vanes are placed at an angle so that water enters without a shock. When we come to detailed design, is where we talk of those vane angles at exit and the vane angle at entry, and what they do portend as far as we are concerned. Okay? This one we must understand whether you like it or not. You see, kuambia mfanye engineering. After all, you came in being the best, some of the best in the country, and we want to make the best out of you for the industry. Nasikia Mazi Mumbi. You have to be the best for the industry, whether you like it or not. Okay. Now, we can have impellers, and the impeller veins, they can be of various kind of arrangements, as you can be able to see. We have those with curved veins or curved forward veins. You can see that in A, curved forward veins. That is how they look like in detail. And it is usually in the direction of rotation of the impeller. In this, you find that the flow of liquid is actually taking place on a concave surface of the vein. And because of the arrangement of the veins, they actually give an efficiency of up to 75%. But still, these are not commonly used. Okay? According to some of the operations, that is a very low efficiency. We don't know whether we will reach our destination with that kind of an efficiency because of the way the curves or the veins are forward. Otherwise, we can have B in our diagram, what we call the radial veins. They have outlet tips in a radial direction, as you can be able to see. The way it is shaped, unlike in A, still the direction is the same, but because of the curving of the veins in a radial way, their efficiency is between 80 to 85%. That is a little bit good. 80 to 85%. That is pretty good for any operator. Otherwise, when your veins curved backwards, like you can be able to see in C, then you are saying that the curved backward veins, or veins that are curved back away from the direction of rotation of the impeller, it will force the liquid out by on some kind of a convex, not a concave now, surface of the pump. And these are said to give the highest efficiency, up to 90%. And sometimes they give slightly more than 90%. You may find them at 92 and 94%, which is a very good efficiency because it's like whatever is your input, you're almost getting it 100%. Whatever is in your input, you're getting 100%, almost 100% of the output. And that is very good. You'll find this is what matters, even when it comes to procurement and you are doing evaluation of the tenders. Check whoever is giving you the best efficiency. And you make sure that on the performance or characteristic curves, the guy is not extrapolating on the graphs or on the curves to give you something to satisfy your curiosity. You have to be solid as an engineer, Mr. and Madam, and you get the best for your organization. Thoroughly evaluated, thoroughly reported, so that you can be able to convince the authorities, if they may ever question why you awarded the tender to the lowest bidder or the highest bidder or just any bidder. These are the things you grapple with, whether you like it or not. Okay, and you must be knowledgeable enough to make good recommendations with a good technical backup report. Okay, so that someone will see the authenticity in awarding the tender, but not someone to think your pockets were aligned. And that's why you awarded the tender to X and not to Y. Okay? still on the same. We've done said that the liquid will enter from the sump through the eye of the impeller, and it enters to the vein at point 1. In this case, I don't know whether this is very clear. And it will leave at point 2, maybe I have one which I'll blow up. Yes, I think I've one here. Can you see point 1 and point 2? Still, this one is not very clear. Yeah, to you guys. Well, the liquid enters through point 1 and leaves at point 2. Where you have the velocities now, because of the arrangement of the inlet into the veins, okay? The inlet into the veins, or the arrangements of the veins and the blades, where you have inlet at point 1 and point 2, depending on how they are shaped, it will be able to come up with a certain velocity. We have velocities that are related. You have V1 at 1, and you have velocity V2, okay? These velocities, as the veins run, you find that tangential to the vein or the impeller at the inlet and outlet, respectively, that is. They also make an angle beta 1 and beta 2. I'll show you those details. With the positive direction of the peripheral velocity, where you measure V1 in a clockwise manner, where you address or you have to worry about the vein angles. Otherwise, when you talk of the total pumping head, H, let me put that statement on it in brackets. Talk of the total pumping head. Okay, total pumping head, H. Okay, let me move this a little bit. Or let me minimize this. I can be able to see. The total pumping head, H, if you allow me, it is given by HS, which is the suction head, and I told you that is in theory. It is given by HS, which is a suction head, plus HD, which is the delivery head, plus HFS. What we call HFS in pumping is actually a factor of safety on the friction head, which does not exceed 0.6 of a meter. So we have it there. Then there is the velocity head due to delivery velocity, or velocity of delivery. We're calling it Vd squared upon 2G, plus sigma HF. Sigma HF for friction losses on the delivery pipe. Okay? Otherwise, to facilitate for enough suction, for the suction, we peg it on the atmospheric pressure. This is H what? H atmospheric, let me call it ATM. Sio ile ya kutoa pesa, Josh Kamau. Najua ukisikia ATM unafikiri ni ya kutoa pesa, si ya kutoa pesa. HATM for atmospheric pressure head. At that point, depending on the average mean sea level, equals to HS. That is the suction lift or suction head plus HFS plus now HV, which is the vapor pressure head, plus now NPSH. NPSH for the net positive suction head. It is the net positive suction head which will account for what we are calling cavitation. It will help you gauge whether cavitation will take place or it will not take place. That's why when you invoke the NPSH, then what comes into your mind? What comes into your mind is the application of what we call the TOMA cavitation number in this. What I would want to tell you is that when you are evaluating for tenders, or when you are carrying out tender evaluation, the key thing you check, one of the key things you check on the tender documents that have been given by the suppliers, and they have been able to mark the performance curves, is actually the NPSH. You tell deliberate, please make sure you mark your NPSH. If someone does not mark the NPSH on the curves, you don't give him that contract. And that's why if they all misbehave or they goof, you may have to go for re-advertisement of the same. You have seen cases where you find tenders are re-advertised because those who did quote or those who did tender, they never met the required specifications. Okay? And these are things that you encounter in the industry. We'll still go to details of this ATM, which Kamau may like it so much. Okay, otherwise, this is an arrangement of the pump. You can see the foot valve, the strainer, the suction pipe. You can see from the free surface of the sump up to the center line of the pump, you have HS, which is the suction head. And you can see the kind of a pump you have. Is it a whirlpool or is it a diffuser type? Or is it a vortex or a diffuser type? Or is it a volume type? The arrangement of the impellers and the vanes or the blades will be able to tell you the type of a pump you have. Madam, you can see the priming funnel still there. I know you don't like it because you think it's a lot of work. But whether you like it or not, you have to prime them. I've not seen a scenario where the pump has to prime itself automatically unless it is a self-priming pump, which are also very rare to come about or to come across. And you can see the other arrangements with the pressure gauge on the delivery side. And you can see the positioning of the delivery valve. And the tank, the overhead tank where that liquid is being taken to. See the positioning of the eye of the impeller and the base plate or the positioning of the pump with regard to where the sump is located. Otherwise, total pumping head equals to HS plus HD plus HFS plus VD, which is the delivery head, plus total friction head. Okay? But when I used to be in the industry, I was mentored by good men. When we used to be in the industry, this is not what we used to do. We used to say total pumping head. Let me borrow this and place it here to say total pumping head hapa na kuibia Syria industry. What we do in practice total pumping head, okay, let's call it H. It is equals to, okay, in reality, it is equals to HD, let me say, I'll say it is equals to HD plus all this, okay, HD plus that, plus HFS. We rarely talk about VD, it is so minor, but we rarely talk about it. Plus sigma HF, plus now, not as equal sign, but plus. No, I don't like that. It is that plus. Okay, let me remove the subscript. It is that plus. That's a multiplication sign. It is that plus. What is it? It is that plus. What I'm going to put in there? Plus what we used to call residual. We used to call it residual head. Used to call it residual head. And let me call it H residual. Let me see. Let's see whether this works. Let me put it the right way. What we are calling residual head. Residual head, we make it a superscript. And then this one I can revert to. Okay. Can you see that? That is how we used to do it in the industry. We used to call it residual head. And that residual head, this one here, if you allow me to borrow it, it's somewhere here. We say this residual head is actually approximately, okay, this one is approximately equal to 10.33 meters. That is atmospheric pressure at sea level. Okay. When you're talking of theories, you don't bring it in. But when you find yourself in that design office, that's why I said my entire life in the industry, I worked in a design office. When you find yourself in that design office, that is how you treat it. To avoid all this business of VDs, doing HFS and all that, you add 10 meters. So that after you have considered HD, let me qualify this HD. Let me qualify this for you. This HD here is actually, no, what's wrong with that? The HD there, let me call it my elevation head or elevation elevation head or difference? What do we mean by elevation head or difference? Okay, if from your levels, the sump is located at 1560 meters, and the elevated tank, or where the reservoir, where you are dropping, where you are pumping to, is elevated at 1720, that is too much, or is elevated at 1650 meters. What's the difference? The difference between the two is 90 meters. So that elevation head for your HD, an elevation of 1650 meters above mean sea level, and an elevation of 1560 meters above mean sea level, you subtract both, you get a difference of 90 meters. 90 meters now, you add to your HFS, which is 0.6. If you care, if you are still interested, you go for VD squared upon 2G plus sigma HF, which is given by the Darcy's-Weisbach equation or whichever it is. You get the total friction head loss, and then you add your residual head. You'll be able to get a total pumping head. Tuko pamoja? You'll be able to get your total pumping head. Now, when it comes to design of these systems, if it's a water supply system or a rising main, a pumping main, what do you look for? You design it in such a manner that whatever diameter, depending on the discharge you are going to get, the velocity does not go beyond 1.5 meters per second. It must have a range between 0.6 and 1.5 meters per second. Beyond that, it is a punishment to the system. Below that is a lot of nonsense. So you have to operate within the limits of 0.6 and 1.5 meters per second. If you look at the Calibrook wide formula curves, there is what we call the operating zone. You operate within that zone in your design, okay? You make sure the velocity does not exceed 1.5. Sometimes you may find if it goes up to 2, well, we still, shingle panda, we accommodate it, but you don't let it go below 0.6, okay? It is good if it ranges between 1 and 1.2, 0.75 to 1.2. That will be good enough, okay? And this is what you come across in practice. Nyinyi mnasikia kina Nyongeza? Nyongeza,
Yes,
can you hear
tunasikia.
me?
Yes, I
Unasikia?
can hear you, sir. Yeah.
I want you to go and work for Davis and Shirtleaves as a sales rep. But make sure you get an upper second or lower second. They will accommodate you. Okay? They go for the best.
Yes.
Yes, that's why I want you guys to get the jobs. When you are done with you work out there. Or Rift Valley Machineries. Okay? They are located somewhere on Addis Ababa Road in Nairobi. Okay, or whichever company. Anyway, so much for that. So this is still the same arrangement. I've tried to blow it up so that you can be able to see the details. Okay? Shaft is driven by electric motor or engine oil. We have settled for that. Otherwise, you can see the volute casing and the priming funnel, which our lady didn't like. She thinks being taught to prime is getting tired. You're not the one priming. You tell your operators, can you please prime that machine before you start it? Okay? Sometimes you have to leave the office and go to the field to see what the guys are doing. Okay? Otherwise, when we go for pump selection, then what do we look for? What do we bear in mind? The type of liquid to be pumped, to pump against. We have already handled that, addressed that. And the demand of water to be supplied. In your public health engineering, are you doing it? Are you doing public health engineering?
Yes, we are.
Yes.
Yes. When you are making computation for water demand, it depends on the class of the population. Is it high class, low density? Is it medium class, medium density? Or is it low class, high density population? Then using the geometrical method, okay, or using whichever other method, you can be able to make computations for your water demand. Okay? Why you have those kind of classifications? Because in the high density, low class, you give those guys a per capita demand of 50 liters per day. Yeah? Medium density, when you are living in Buruburu, you are given 150 liters per day, per head per day. When you're in high class, low density, you are given 600 liters per head per day. Now that sends you back to the animal farm. All animals are equal, but some are equal than others. Anyway, you look for the demand to be supplied. That will give you the amount to pump. You look for the source of water. Is it a well? Is it a dam? Is it a river? Is it a spring? Or what exactly is it? You look also for the altitude. Okay? That is what I was telling you. What do we mean by the altitude? In this case, I'll put it in this form. AMSL. Average mean sea level. Okay, what is the average mean sea level? All the way from Mombasa to Timboroa. All the way from Mombasa to Mount Elgon. All the way from Mombasa to Kapenguria. Because the belief is that the land is rising from the sea towards inland for the altitude. So we select pump on the basis of all this, the type of liquid, the head you're pumping against, the demand or the total demand for the water, the amount of water which is required to be pumped, the source, is it a well, is it a river, is it a dam, is it a spring, is it a what? All that you have to address yourself to. Then, using your altimeter or using your GPS, you determine your altitude above mean sea level. That matters so much. Because when you're doing a feasibility study, you walk around with your GPS, or you may walk around with your altimeter, which will be able to give you the elevation at any given point as you walk. That is during your feasibility study, or when you are doing your reconnaissance survey. Then after that, what do? You compile the data for purchasing your pump. And when you are doing that, you fulfill the following requirements. And when you're fulfilling these requirements, though I've mentioned it there, some will say specific speed is the main factor. Specific speed, you actually derive it from your dimensional analysis, your physical modeling, from your true and your distorted models. So this is where you find what we call the specific speed. which is dimensionless. We'll come to that in your dimensional analysis. Then the following, you find it important. You address the reliability of the service. What do we mean? The last time you purchased from Davis and Shatcliffe, how did they treat you? Did you call them during the warranty period and they refused to come? Did the machine break down even after working for 2 days? What is the initial cost of the plant? And what is the efficiency of the plant? Is it 75, 80, between 80 and 85, or is it over 90? What about the depreciation of the life of the pump? If you have done a plant as a unit, I don't think plant as a unit is in your syllabus. Most machines depreciate at a rate of 33 and a third percent. Okay? You look at that against your maintenance and the period of running that machine, then you will end up knowing whether the machine after 3 years you should throw it away, get another one, or you should still continue with it, because you keep a data of maintenance cost against what you purchased it for. And if you draw that curve and you discover the maintenance cost curve is overshooting the initial cost, then there's no point of keeping that machine. You dispose it off. So that's why we talk of depreciation, or the life of the machine, or the life of the pump. Okay? These are things that we normally address. What about the cost of energy to be used in running the pump? Are you using diesel? Are you using solar? Are you using electric energy? If you're using electric power, how are the bills at the end of the month? Because it must be coming to you. If it is a water supply you are running, how will be the bills at the end of the month? And remember, when you designed some of these systems at the initiation point or the initial stages of coming up with a project, someone must have looked at the economic aspect of the project, or the financial viability of the project. If it is from a financial viability point of view, are you making the money, or you are throwing the money into the ditch and the operatives are running without salaries? Okay? Is that what you are doing? If it is economic viability, are the farmers having ample time in their farms to produce more, or they have to spend hours on days on end looking for water because Mr. Engineer Alan Kiprotich made a bad design? Kiprotich, nakuonea. Okay, Mutai made a bad decision. Or Njuki made a bad decision. So you look at the cost of the energy to be used in running the pump or the machines, and then at the end of it, overall, the maintenance cost. How are the breakdowns? How are the pipes bursting? The engineer made a poor design. He never addressed water hammer. And every time they're operating the system, there's a burst. There's a pipe burst. Or is it like in Maasai land, where they'll come with their spears and pierce the pipes if they are plastic, or if they are PVC pipes, so that the animals can drink? I remember like the Kilimanjaro project all the way from Nodresh up to the river. The Maasais went with their spears and decided to mess up the pipeline. And then they asked, why have you done this kind of thing? They said you cannot take water from Nodresh, which is at Mount Kilimanjaro, all the way to the river, and there is no outlet for our animals. Maybe somehow it made sense. But when it comes to design standards, the rising main or the gravity main is not supposed to supply anyone on the way until the water or the liquid reaches the main reservoir. From the main reservoir, you can arrange for redistribution to where the liquid is required. Otherwise, when you're compiling data for purchasing a pump, these are some of the things or some of the considerations you look into. Okay. Now, what about when you're ordering for the pump? You quote the number of pumps you need. Are they 2 or is it 1? If there are 2, one for use and the other one is for standby. You also quote the prime mover. Is it electric or diesel? What about the capacity in cubic meters per hour or cubic meters per second or per minute? That you have to tell Davis and Shartleaves how much it is. You tell him the number of pumps you need. You tell him the prime mover you need. You tell him the capacity in cubic meters per hour, per minute, per second. And you tell him also the total lift. You sometimes have to tell him the length or the size of the suction and delivery pipes. And then you tell him the type of a pump you need. Is it horizontal or vertical? Is it submersible? Is it for raw water or treated water? These are things that you address. What about the liquid you're handling? Is it coffee pulp? Is it sewage? Is it sugar, molasses? What? What kind of a liquid? Is it fuel? What kind of fuel? All these things you have to address, the type of liquid. Then after that, you mention the place of application. Is it irrigation? Is it for a condenser circulation? For boiler feed or deep wells? All these are details you have to address when you are ordering for pumps or when you are asking for quotations, when you are preparing your tender documents. So that you say tenders are requested for supply of A, B, C, D with A, B, C, D, E, F, G, H details. Okay? And you give another specifications as far as the tender documents or the request is concerned. Okay? Any questions on that, ladies and gentlemen, before we move too far? Hey, are you there, guys? Huh? Josh, are you there?
No question.
Yeah.
Don't be mesmerized, Buana. This is what you are going to face out there. If you thought it was a bed of process. Eh? Collins Omondi, unasikia? Collins. Where are you, Collins? Nyongeza uko sawa? Hmm?
Niko sawa.
Why is Collins quiet? These are things you come across whether you like it or not. Thank God ukimaliza utakuwa ukibebwa back left. You may be lucky to be carried back left, not with the others. Okay? Otherwise, having seen how we can be able to make a tender or prepare tender documents. And by the way, in the next cut, I will ask you to prepare me tender documents so that we can buy these pumps. You buy me from Davis and Shartleaves or whichever company. I would like to see how you can prepare tender documents because that is part of you. How you can prepare the specifications, prepare tender requests, and you can take it for the advertisement in the local dailies. I've already leaked that. That is a leakage. Okay? So with that, ladies and gentlemen, it is 1640. And I don't want you to get too much and it becomes things fall apart and no longer it is. Let us stop at that. We pick it up next time. We'll make sure we have dealt with this as we speed off towards serious matters with the pumps and turbines. So any questions for today? Once we are done with this, I'll get you the notes like I've done. Otherwise, I will also check with the mechanical labs to see what facilities we have. We may take a tour there one day, one of these days, so that we can look at the realia, the real things they have, if they have any, or the models they have in the lab. You can touch it, you can feel it, you can dream about it. Otherwise, with that, thank you so much. Wish you the best. Have a nice week. Keep away from trouble. And if you have been elected an official, kula pesa pole pole. Usikule haraka sana. Otherwise, thank you so much, ladies and gentlemen. Bye-bye for now till we meet again.